Hey, Aurora here with Supercharged Science, and today we are going to do a homeschool science class just in sonic vibrations. And if you like this and you want more, you want to go to my website, which is www.superchargedscience.com. It has a ton of science educational hands-on experiments you can do for kids K through 12. So let's go ahead and get started. We are going to cover we're going to kind of build on yesterday's topic, which we talked about astronomy and astrophysics, and we talked about how light can shift, especially if that light source is moving. We're going to take that over and explore that when it comes to sound waves, because a lot of people have a lot more everyday common sense about how sound waves and water waves really kind of work. So let's talk about the Doppler shift and sound specifically here on the planet. Now, again, my name's Aurora with Supercharged Science. If you like this and you want more, I have a whole host of more science experiments you can do with your kids at home. Super easy, uses everyday materials. Just go to my website, www.superchargedscience.com, and you click on free stuff, and then it just automatically comes to you. It's like magic. Okay, so I'm going to share my slides with you. So for today, we're going to talk about sound. So sound is directional. Now, what do we mean by that? You have any ideas? Can you tell me out loud? Okay, so sound is directional, which means that it matters which way you're facing, for example, when you listen to live music, right? It's going to sound different depending on where you are in the room. Now, try this right now. Stand up and walk around while I'm talking to you, okay? So this isn't going to work if you're just listening to me with earbuds on, obviously. You actually have to get up and make the speakers go, but you can hear me, right? Get up, walk around. Do you notice how I sound different depending on where you are in the room? What if I get up and move around, right? What if I move my microphone around? Yeah, I'm gonna sound different, right? So we call that direction. So sound is directional. Now, if you've ever played with like a megaphone, like this kid is, parents are thinking, oh no, not ever in my house. Then you probably already know that it matters which way you point the cone, right? So sound travels in a straight line. Now, I want you to listen to this next bit first, and then I want you to tell me what's going on. Are you ready? Okay, here we go. So why is the siren doing that? Oh, sorry if that was a little jumpy. It looked like it was a little choppy there. But why does sound do that? So basically any source that is giving off sound waves, if it's not moving, those waves propagate out, they move outwards at a steady rate. But if the source of the sound is moving, then that's called the Doppler effect. And it works for all kinds of waves. It works for light waves, visible or invisible. It works for water waves. You've probably seen waves bunch up in front, like on the front of a boat, if you're slowly trolling through the water. And it kind of looks something like this. So the same thing's going on with sirens. When the police siren is coming towards you, here's you, or the ambulance is coming towards you, those waves are going to bunch up on the front. And what that means is, and they're going to stretch out behind. Oh, you're not even seeing my slide, sorry. So when they bunch up in front, it's basically going to make the pitch increase because now the wavelength is shorter, and so that's a higher frequency, a higher sound. So it happens because the source of the sound itself is moving and bunches up the waves in front, stretches out the waves behind it. Since sound travels in waves that take time to get to your ear, if the sound source itself is moving, that's going to affect what you hear. Okay, so if it's light, it's going to affect the color. We talked about that yesterday. If it's sound that you detect with your ears, that's going to, you're going to hear it either higher pitch or lower pitch. And that's why you heard two things going on. You heard the do-do-do-do, right? It was high pitched. And then as it passed you, it started to go through transient stage. And then as it passed you, as the siren passed you, it actually stretched out and got lower and longer. Do-do-do-do, right? So that's what's going on. Okay, so why is that important? Well, for example, if you have a green light that's moving towards you, it's going to start to look more blue. If it's moving away from you, it's actually going to look more yellow. If it moves really fast towards you, it's actually going to shift even more. So if it was like a green light, now it's going to shift even more to the whoops, did I say that wrong? So if it's green light and it's shifting towards you, it's going to shift even more blue and violet. And if it's shifting away from you like a star, there is no such things as green stars, but if there was a green light and it was moving away from you, it would shift more into the red. Okay, so if you look at the ambulance here on the bottom of the slide, you can see here that since the siren itself is moving, it scrunches up the waves, right? And so if this was light, it would look more blue if the star was coming towards you and more red if the star is moving away from you. We talked about that yesterday with Doppler shift. That's actually how astronomers know whether a star is approaching the Earth or moving away from it, right? Okay. So diffraction is how sound bends around objects or through openings between barriers. Now you've probably seen diffraction occur like if you're looking at water waves and they're going through a gap or a wall between logs like you see in this picture here. This is an aerial view here of water waves. You can see diffraction happening. It's the bend around an object. Have you ever tried this experiment? You ever tried to speak with someone who's standing just outside the doorway? Even if you can't see them, they can hear you, right? Because the sound waves from your voice bent around the doorway to that person. And actually, if you try that tonight, there's actually a sweet spot that they can hear you really well because they're just in that perfect spot. Oh, and so diffraction is also why you can still hear totally fine at a concert if you're behind a huge pillar, which is why it's so easy to hear conversations in the next room, even when your parents don't really think that you can hear them, even though you've got better ears than they do because you're just younger. Even though they can't see you, their sound waves are diffracting around doorways or around open windows, and you can hear them just fine. Parents are like, oh no. So animals use this idea to communicate over long distances. I mean, think about the places that most animals live. They're either in the forests or in the mountains, maybe in a swamp or the prairie. All of these places have tons of plants and rocks in the way, right? Trees. But animals can still get in touch with each other because they make sounds that can be heard even when you can't see them. So the sound waves are going to be bending around obstacles and to travel where they need to go. Okay, so people can hear between 20 hertz to 20 kilohertz. That's a range. Sounds above that are called ultrasonic, and bats use high-frequency ultrasonic waves called echolocation to detect objects in the air, because if they use lower frequencies, the waves would diffract around their prey and then they'd never find dinner. So here's what we're looking at here. So you see the dolphin in the water. Is that a dolphin? I think it's a dolphin in the water. Okay, so basically bats use sonar to detect objects. So if a bat screams, it goes, ah, right? But in a frequency you can't hear, and it never comes back. What does that mean? That means nothing's there, right? So humans can't usually hear these sounds unless they've slowed that down into our hearing range. But insects can hear them. Moths and crickets and beetles and whales and shrews and all kinds of birds use echolocation. Oh, I mentioned sonar. Okay, sonar uses sound waves to find where stuff is underwater. You can see it happening right here in this video. Sometimes animal echolocation is also called biosonar. Oh, now animals at the other end of the spectrum, like elephants and whales and hippos, they actually can create infrasound, which is the sound that is below what people can hear. Things like earthquakes and avalanches, those are also examples of infrasound. Okay, you can kind of see a bat doing it there, huh? Now, this is just a simulation. A bat, you wouldn't actually see a bright spot of light in front of the bat. He's looking for dinner. Okay, so when an earthquake happens, it's not just on the surface of the earth. In fact, earthquakes happen deep in the earth, and then we like to find, let's see if there's a picture. No, it's not on this picture. We like to find where draw a point from wherever it started in the earth to the top. And sometimes it's just under the mantle, but we like to draw a line to the top to find the epicenter. So if you've ever been through an earthquake, you know how nerve-wracking it can be when then there's like a sudden low rumble and then things start to move and shake, right? And you might be wondering, why don't people let us know in advance about earthquakes, right? We know about tornadoes and we know about hurricanes, but for some reason, we can't really detect earthquakes. That's because when the plates on the surface of the earth start to move, they pull apart or slide against each other or smack into each other, and that's what the earthquake is. There are these plates that are floating on the surface of the earth, right? So there are also earthquakes above ground as well as underwater and on the ocean floor. So when an earthquake happens, it's actually not usually on the surface, as I mentioned. It starts in the interior and radiates outwards. Now we can totally get sidetracked and talk about earthquakes for the next hour, which is super fun. But if you really like earthquakes and you want to do like seismology and find out where the epicenter is and use all kinds of tracking and do like real data analysis, that is actually in my online eScience program. So you can check that out. It's www.superchargedscience.com/easy. Like, wow, that was so easy. She's teaching my kids. I don't have to teach them, and they now know more science than me. So superchargedscience.com/easy, and there's a whole section just on earthquakes and tectonics. Okay, so let's get back to sound waves. So basically, the different kinds of waves, there's P waves and S waves. We're not going to get into that, but basically what I want you to know is that the waves move through the earth just like sound waves move through water, just like the water waves move on the surface of the water. It's the same thing, same wave, and they still follow the same rules when it comes to how they propagate, how they move around and inside this earth as well as along the surface. Okay, what happens if you have something that generates sound, but it moves faster than the sound wave itself is traveling? So this video that you're seeing now, this is an animation that shows you a jet that's moving at 3 different speeds. Now this first one is subsonic. It's going slower than the speed that the sound waves are moving outward at. Notice how they kind of bunch up in front of the jet, just like the water ripples if you moved your hand in the water. Water is just easier to imagine because it's not invisible like air, right? Okay, now the second one, the jet is moving at the speed of sound. It's called transonic. So the waves are so bunched up in front of the jet that they are on top of each other, and that's what a shock wave is. It's formed a shock wave. The jet is breaking the sound barrier. See this image at the top? This is a jet that's breaking the sound barrier. Okay, now this last one is obviously it's moving faster than the speed of sound, okay? So these two at the top are breaking the sound barrier. So the water in the air is basically condensing at the shock wave, and it's coming out and forming a huge cloud because there's a huge pressure jump across that pressure boundary. Remember, sound waves are pressure waves. And when you stack a lot of them on top of each other, you get a big jump in pressure. So here, let's see. Oh, we didn't talk much about the supersonic one. Supersonic just means it's traveling faster than the wave speed or the speed of sound in this case because it's moving through air. So you get this cone-shaped thing. And that's actually something I did my master's degree in mechanical engineering. I actually studied supersonic and hypersonic flight. Hypersonic was when you go above Mach 5. So Mach 1 is when you are breaking the sound barrier, and so Mach 5 is 5 times the speed of sound. So all kinds of fun and interesting things happen. Like basically it turns science inside out. It's really cool. So shockwaves, what are shockwaves? Shockwave is a sharp pressure change in pressure that usually is made by moving faster than sound. You can see shockwaves as dark lines when they're imaged right. This is a special kind of photography that will pick up the air density. So you're actually looking at air. This is a sharp pressure wave. So it'd be invisible to your eye, but when you look at it with a certain kind of photography that picks up different changes in density of the air, you can also see the turbulence in the air here. This is what the air actually looks like. It's normally invisible, but again, with this kind of photography, it's just schlieren. This suddenly becomes visible, right? So do you see the fighter plane here on the bottom right? Now you know why fighter planes have swept back wings, right? Imagine if this thing had huge wings, right? They would break off when they pass by, if they were to extend beyond this pressure boundary. So over here is atmospheric pressure, like you and I are experiencing, but right off the tip, this is because the aircraft is going faster than the speed of sound. And so you've got a big boundary. So it's regular pressure here, but this is a big jump in pressure here because all the waves just bunched up on the front and now formed a solid wall in the air. So the wings would shear off. So these weapons, when the sharp relation pressure breaks, releases after the buildup by the shock wave. So as this thing is going, there's a big cone coming out of it, just like this cone, and your ears are in regular atmospheric pressure here. But when this thing is past you, then when this barrier hits your ears, that's when you hear a boom, and that's that pressure, change in pressure that you can detect. Now there is an animal that is supersonic. It's actually the pistol shrimp. It makes a sonic boom of its own. Every time its claws snap so fast, every time the claws snap together, they go so fast that it shoots a 60-mile-an-hour air bubble at its prey, and that's how it stuns it. Isn't that cool? Here, let me play it again. So there's the air bubble, and see the air bubbles forming. So it doesn't actually grab the prey. It generates an air bubble that stuns the prey, and then it can go get it. Would you like to travel supersonically? Wouldn't that be cool? You actually can. Actually, you've been able to since 1969. The first supersonic transport aircraft was developed. That was the Concorde. There were about 20 of those, and it was pretty much just about the only way you could fly supersonically, but it went about twice the speed of sound. Russia also operated a passenger airline that was supersonic, and for about 27 years, people flew supersonically. But it was like 30 times more expensive than a regular plane ticket, so most people didn't do that unless they were like business class and super important and had to be places like faster than regular people. Normally, it takes a regular airplane about 8 hours to go from New York to London, but in one of these things, you could get there in about 3.5 hours. There's a new version now, the Concorde 2. It's actually able to vertically take off and land, and it has the ability to fly 3 times faster than the original. So now you can just get to London to New York in just 1 hour, and you go about Mach 4.5, about 4.5 times the speed of sound. That's almost hypersonic, right? Okay. So hypersonic flight is through the atmosphere. In our atmosphere, there's speeds above Mach 5. It's about 5 times the speed of sound. And I pick 5 because at speeds above that, the air starts doing like really weird things, like splitting into smaller particles and melting the wings off of airplanes and stuff like that. So hypersonics is its own set of studies. Okay, so I'm going to pause there just for a minute because we covered a lot. We covered Doppler shift, we covered different kinds of sound waves, we covered subsonic, transonic, and supersonic, and a lot of different things. Now, this is just a small portion of the big 1.5 hour class that's available in my online eScience program. So if you'd like this and you'd like to do more, you want to go to www.superchargedscience.com/easy. Like, wow, that was so easy. She got to teach my kids for me, and now I got all this free time, and now they know more science than I do, and they're asking me for supplies, and I just turn it around and give it back to them. Because a lot of the, you shouldn't have to spend a fortune in order to do science. I mean, how many science kits do you really need? Honestly, it actually hinders kids and puts them in a little box of creativity because they are limited by what the science kit has and what the directions are. And if they snap a piece and break it in two, which usually happens, or there's pieces missing, now suddenly they can't do the project and oh well, right? So instead, by doing hands-on experiments that use popsicle sticks and paper clips and tape and scissors and duct tape, engineer's best friend, you can actually show your kids how to innovate and create and design just using everyday stuff. Because honestly, that's what real scientists do. They don't have, well, most of them don't have these custom made parts. They have to use what's already off the shelf because it has to be cost efficient, it has to be effective at what it does. And sure, they're designing new parts every day, new different kinds of carbon fiber materials and all different kinds of aluminums and all kinds of alloys. But at the end of the day, they're still using what's available on the planet. So being able to teach your kids in a way that's sustainable, where their imagination is only limited by what's in here, not what's out here, is one of the real keys to giving your kids a solid science foundation. So one of the things we do with my online eScience program is we will show kids, we'll give them information like we just did, and then we'll give them hands-on, step-by-step instructions for doing several projects, and by several I mean dozens. And then they're very open-ended. So at the end, I'll say, hey, this is the basic idea. We're making, say, for example, a slingshot harmonica. And now I want you to make it even better. Now improve it even more. So it's very open-ended because honestly, one of my moments with textbooks is they'll say step 1, step 2, step 3, and expect this answer. And I don't know about you, but no scientist in their right mind is going to do an experiment they already know the answer to. Science isn't about what you know. It's how you handle all the new stuff, how you create, how you innovate, how you solve problems, how you think. And so my eScience program is very different from a lot of academic curriculums out there because it's designed from the inside out. We get kids interested and excited about a topic. We get them their hands-on. We show them things that are just ooh, wow, and fascinating and inspiring. And then we give them just enough so they have a taste of what's possible, and then we let them go because we've given them enough of a foundation. You got to give them something. You just can't say, hey, go learn science on your own. There's the whole world. Good luck. You have to have some kind of framework. So we give them that. And then after we give them the foundation, we give them the basic ideas. Now we say, hey, can you make the plane go 3 times as far? Can you design a helicopter that goes 5 times as high? Can you shoot a rocket down the street? And this goes 100. Can you make it 200? And then we give them so much support and guidance for this process. Which reminds me, how often can you ask a textbook a question? Yeah, right, like never. So these academic writers that mean well, that write textbooks, have no connection with their audience. And so in my online eScience program, anytime you have a question or a problem, that's what you type it in, and me and my team of scientists turn right around and answer it for you. In fact, just yesterday, I was helping somebody pick a microscope. They had a budget, they knew what they wanted something that would last through high school, and they wanted a recommendation. I gave them a whole page that we had already reviewed and looked at different microscopes based on their goals. Somebody last week wanted to get their kids a telescope, and actually I talked them out of it because they're expensive and you don't know where to point it. What's even better is a pair of binoculars that you already have around the house. The point is that you can already do solid science, and as a parent, you don't have to be the teacher and you don't have to know all the answers. Your job is to be super excited for your kids and get them interested and excited about a topic just by giving them the support that they need. You don't have to do it all. I don't know how to speak German. Why would I teach that to my kids? I don't know how to play tennis. I wouldn't teach that to my kids either. I would find somebody who's passionate, excited, I can do a way better job than me. And I would focus on the things that I'm really good at. So Supercharged Science, super good at science. We do science in chemistry and biology and life science and physics and earth science and you name it, we've got it covered for K through 12. And you can actually give us a try for 30 days, risk-free. You try it, if you like it, great, you're part of our science family. If you don't, hey, no hard feelings. You just request a refund within the first 30 days, no problem. And then you can try something else. Maybe you'll get some distinctions about what really works and maybe what's not up your alley. Okay, so if you like this and you want more, you want to go to www.superchargedscience.com/easy. Like, wow, that was so easy. And you can go there and it's got a video of me showing you exactly what the eScience program is and what it'll do for you and your kids. If you have any questions, feel free to send me an email. I'm a real person and my company is staffed entirely by human beings. And so you can go to, you just send me an email, aurora@superchargedscience.com, and I'm happy to answer that for you. And actually, people give me all kinds of great ideas all the time. So if you have one, I want to hear it. In fact, our top seller is marine biology, the marine biology curriculum. And that actually came as an idea from someone about 4 or 5 years ago. She called in and said, hey, I love your stuff, but my kid really loves marine biology. Do you have anything in marine biology? And I thought, what a great idea. So I did research. It turns out there's only one course on the entire market, at least there was at that time. I think it's still this case, maybe 2. And it's a 12th grade course. I don't know about you, but by the time my kid gets to 12th grade, I need to know if they were interested in marine biology like way before that. So I made a course. Originally I started it for high school, and then I'm like, let's do junior high. Let's include that as well. And then I decided, let's just make it K through 12. So I would say it's about 2nd grade and up. And so she came up with the idea, we developed it, tested it, had tons of people try it out, give us feedback on it, and now it's one of our top selling products. We also have a whole course in civil engineering and in aviation and in chemistry and chemical reactivity, what it's like to be a real chemical engineer. Somebody had the idea of what's it like to be a geologist, so we made a whole course in that. So we have a lot of career-based science curriculum now based on the feedback from our science family members. So we're loving all the feedback that we get so we can make things that are actually useful to you. So, all right, long story short, I hope this class has been useful. I look forward to seeing you next time. I'm going to post the classes we're going to be doing. Next week's a holiday, I know, but we're going to be posting the next couple of classes that we're going to be doing. And if you're interested in becoming just part of our family members, just get on our mailing list so you'll get a private invitation invitation to my free 1-hour classes that I do. We don't post them anywhere. It's just something that we email to our subscribers as a thank you for being a subscriber. And I'll do a 1-hour class with you and your kids right from home. And it uses, again, everyday materials. So I hope this has been fun. I hope you learned a little something, and share it with other people. Let's make this world a better place by sharing our knowledge and helping others just get the science education that they really deserve. I will see you guys next time. Enjoy your weekend with your kids. Take care, everybody.